All right, go ahead.
And we are back. Welcome to chapter 14, part 2. More on NMR. We're trying to figure out how we know what we've got. So that's the main thing, these last couple chapters. Mass spec, IR, together with NMR, nuclear magnetic resonance, we're figuring out how do we know the structure of what we're working with here. This is for April 3rd, Friday. Quiz 8 is also due tonight. Make sure you upload that by well before midnight. The Learning Suite's been working well lately. Homework 14 is not due until Monday, April 6th. We have another class period on chapter 14 coming up. Now, keeping in mind NMR, just to review, there's 3 key things you've got to keep in mind here. Don't get bogged down in the details of this. We approach an NMR problem and we extract the information sequentially. These are the 3 key things to keep straight. What is the shift or the delta value for that set of equivalent protons? This is the type of hydrogens involved within a molecule. That's the first thing, delta here. Remember the ppm range is 0 to 10 for proton NMR. The next thing we look at is how many hydrogens, the number in each set. We call that the integration. Now that will be a ratio number. It's an arbitrary number, but it's a relative amounts. We have to look at the molecular formula and figure out how many hydrogens are in each set. But from that integration, we can know the number in each set. And then the coupling or the splitting of values, the J values, J is in hertz. That's how far apart the little multiplets are. Multiplicity factor, and this is the n+1 rule, where n is the number of neighbors. So that will split a given signal by the n+1. So if it has 1 neighbor, show up as a doublet. If it has 2 neighbors, they'll show up as a triplet. And we'll see that today. We'll be going over that today. So our first graphic up there, kind of to get you highlighted here, what we're looking at is tert-butyl methyl ether up here, the formula shown there. Well, it's a structural formula. You see the tert-butyl and the methyl are on the ether here. And you see a single singlet at 3.2 ppm for the methoxy group, that methyl there. And then these methyls here on the tert-butyl are distinct. They're all the same. Shows up as a nice singlet right here at 1.2. Then you see the TMS reference. Remember what that is? Tetramethylsilane. This is in solution. We use a solvent that doesn't have any hydrogens. We use deuterated chloroform. Sometimes you see a little bit of residual chloroform peak at 7.2 ppm. Chloroform is one of the molecules we'll look here in a second. But notice the scale, 0 to 10 ppm scale or the delta scale. The ppm refers to the number of frequency numbers for each ppm. If this is a 500 megahertz instrument, each ppm range has 500 hertz in it. Now that will have an important consequence for this coupling, the splitting values. If we were at 300 megahertz, each ppm would have 300 hertz. So the bigger the magnet, the better the resolution. And the signals tend to separate out a little better. I'll show some examples of that and talk about that a little bit more. But here we're increasing the frequency value, and that's the frequency of the radio frequency that needs to be applied to tip these signals out of resonance with the external magnetic field. So that's a little bit review of the physics, but don't worry about that. The instrument's quite complicated and expensive due to the precision of the RF frequency generator and the sensitivity of the detector that needs to go. But this printout and how it relates to the structure, that's the topic of what we're talking about. Now last time we left off with this over here. We were looking at a number of molecules and we were determining what? The number of sets of hydrogen signals we'd expect in the proton NMR. We already did this one, I think, dimethyl ether here. These 2 methyls are equivalent, so what? 1 set there, right? If we have dibromoethane, these 2 here are also the same. There's a lot of symmetry there. So again, 1 set. Here's the one we just looked at, just to look at the tert-butyl methyl ether. you should see that, yeah, these would have different shifts because this methyl group's right next to this oxygen. We'll get into that in a second. And the terpenes, you see, have this quaternary carbon insulating it from the oxygen. So there's two sets there. We just saw the two. How about this, toluene or methylbenzene? Now be careful here. How do we add up the sets? Well, this methyl is obviously distinct from the 5 aromatic hydrogens. But these two here, you see, due to symmetry, would be the same. So we have 1, 2 sets. And then these two here, that are 2 carbons more away, that would be what, a 3rd set? And then this one here would be what, 4th. Okay, so 4 non-equivalent sets. However, alkyl benzenes or monosubstitute benzene, these 5 will tend to show up at the same spot because these differences here of where they resonate tend to be right on top of each other. So a lot of times we'll just see 5 hydrogens for the integration there and then 3 hydrogens up here for the methyl. So the integration is important and where these shifts will be. So we'll get into the shift values for aromatics, but these will all tend to be right on top of each other unless you have a very high field magnet, like 600 megahertz magnet, where you have 600 hertz for each ppm, and then these 2 hydrogens will be distinct from these 2 and those 2. So when we talk about these sets, sometimes it's kind of a theoretical thing. What we see in practicality is just 2 sets here, but in theory, and that's what we'll go out just looking at the structure. It should be 1, 2, 3, 4 sets, okay, in theory. Anyway. On a molecule like this, we have what? Dimethyl, what is this? Heptane, and it's what? 2,6-dimethyl heptane. And we see a lot of symmetry in this molecule, right? So actually these 4 methyl groups are all the same. So that's 1 set. And then these 2 methynes are the same due to the symmetry, 2. These 2 methylenes, that's 3. And then the methylene in the middle, that's different than the methylene here, right? So how many sets do we have? 1, 2, 3, 4 sets. Okay, so look at the symmetry there. How about tert-butylbenzene? Same thing as toluene. You'd say these 3 methyls are just 1 set, and then 1 set here, another set there. So again, 4 sets. Okay, unless you have a real high resolution, high field instrument, you might be able to tell those 5 apart. Anyway, let's see. Ethyl bromide here, obviously 2 sets. And then propyl bromide, 1, 2, 3 sets. All right, let's look at a little bit more detail on this one here. And let's talk about topicity. And when we talk about topicity, we're meaning in a practical sense exactly whether the hydrogens are magnetically equivalent to each other. So this is more detail that we need to apply to figure out exactly how these things relate. So if we have this molecule, and let's just look at 2 of these hydrogens here in dimethyl ether. Those 2 hydrogens, we say they are the same. We've got the symmetry here. But let's apply something called the deuterium exchange thought experiment. If we exchange one of them with deuterium, we get this structure. And let's exchange the other one in a similar fashion here, where we have the one in the back with deuterium on. Okay. Now let's examine these 2 deuterium exchange compounds. And these can be made, okay, but then we compare the 2, and what do we see here? Well, if we just rotate around here, right, this is a methyl group after all, that other hydrogen's still there. We rotate around, we see that these are the same. Well, how are they the same? We say they're homotopic. And that means they're always the same under all conditions, okay? So no matter what we expose that molecule, those 2 hydrogens, in fact all 6 of them really, we can exchange them all with this deuterium exchange idea. They're always the same under all conditions. Now, this is kind of a subtle effect because let's go to this guy, this ethyl bromide that we just looked at here. Now, we have the 2 non-equivalent sets, but what about these 2 hydrogens here in the methylene? This topicity idea has a lot to do with these with these methylene groups. You'll see why in a second here. Let's do the same deuterium exchange experiment here. We'd have one deuterium coming out at us. And we'd have what? The other one, which would be in the back now. What's the relationship between those two structures? Here they were the same, right? We could just rotate around this carbon-oxygen group. But now, what do we get? Let's look at that. This becomes what? This becomes a, what? It has 1, 2, 3, 4 different groups on it. So what is that and that? Anybody? That's right, it's a stereo center now, okay? Has 4 different groups on it. So this is our thought experiment, just putting deuterium on there. So topicity-wise, these are not the same under all conditions. These are what? Enantiomers of each other. So what do we call these now? These are enantiotopic. So topicity is change. That means they're the same under most conditions, except when there's something chiral complexing it, like a chiral protein or a chiral catalyst or any kind of a chiral complex. And there are chiral shift reagents we use in NMR where these enantiotopic hydrogens actually split out into different spots and they can become different groups. But if we're under a normal solvent here, if we're in deuterated chloroform, that's an achiral solvent for our NMR experience. So these are the same under those conditions. If it had a chiral complex that it was in the presence of, then these enantiotopic signals would be different, okay? But these are the same right now, although you should note that these two are enantiotopic. Whereas here, all these hydrogens are what? Homotopic, okay? Based on our deuterium exchange experiment. Now let's get the other one here. You can kind of tell if we have enantiotopic hydrogens on a methylene group, what can we also have? That's right, diastereotopic hydrogens. And that's the next one here. Say we've got this molecule. You've seen this molecule before, right? 2 butanol, and this is what, the R version? Doesn't matter whether I have R or S. We have now a pre-existing stereocenter in this molecule. Let's do our exchange experiment on these 2 hydrogens here and figure out their topicity. That's the key thing. Notice we have the methyl groups on the end. These are always what? Homotopic to each other, okay? So we don't need to worry about exchanging those. Those would be the same thing. But let's go ahead and do our thought experiment here. If we got deuterium in the front, notice we still have that R stereocenter for the alcohol, versus what? If we had that same stereocenter for the alcohol and then did our experiment exchange here with deuterium, what's the relationship between those 2 molecules? Before, with ethyl bromide, they were enantiotopic, okay? Or enantiomers, 2 images there. So the 2 hydrogens on the methylene group are enantiotopic. But what about the 2 hydrogens now on this with a pre-existing stereocenter? Notice any conformation we draw here, this deuterium is always in a different magnetic environment than this hydrogen here. So what do we say, the relationship between these 2? That's right, they're diastereomers, so the 2 hydrogens here that came from that are diastereotopic. And what this means in the NMR is they're not the same ever. So they always show up at different spots. So how many sets of hydrogens do we have for 2 butanol? We have this methyl, we have this hydrogen, we have this hydrogen. Wow, we're already up to 3. And we have this methyl over here, 4. And then what about these 2 here? Well, we count them what? As diastereotopic. So we have 1, 2, 3, 4, 5, 6 sets for that. And diastereotopic hydrogens, if there's a pre-existing stereocenter, that's what you look for. And then all the methylenes in theory will be diastereotopic, will not be the same. Now, if you have a lower resolution instrument, a lot of times the frequencies will be the same for these, but oftentimes it'll be more complicated. You'll see multiplets for these two things here, okay? So we'll see some examples of that where it makes it a little more complicated, the topicity-wise. Now, let's revisit this molecule. Now, before we said, you know, we had this, what, 1 or 2, 6-dimethyl heptane, and, you know, these 4 methyls were all the same. Let's put another methyl right there. How many sets do we have now? Take a minute, maybe even pause your video and count up how many non-equivalent sets you expect for that. All right, we're back. Let's see if you got the right answer. Now, we've got a stereocenter right here, right? So these two right here are what? Diastereotopic. So are these two right here. And of course, this one and this one are different also now. We don't have the symmetry anymore. We have this extra methyl group at the 3 position. So how many are we up to? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And what else do we have here? We've got these two, which technically also, because of this stereocenter, the methyl groups can become diastereotopic also now, and it becomes quite complicated. So what do we have? How many? 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12? Now that's a very complicated problem. And the topicity, you're probably starting to see how the methylene groups, due to the presence of a stereocenter, can be different. There'll always be different shifts there. But these 2 methyls here and the 2 methyls here, which are also different, makes this a very complicated problem. Now in the NMR, we probably won't see these all split out into 12 different patterns. So it might be different there. Did I get the right number there, Isaac?
I was wondering, maybe there's 10, because aren't the 2 methyls on the right side equivalent and the 2 on the left side equivalent?
Well,
so those 6 would be the same, maybe?
Yeah, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
Yeah, and that's probably what you'd see. But technically, these 2 here, because of the presence of that stereocenter, even though this is pretty far away, it probably won't split up. So maybe we'll say 10, 12 in theory. Probably only see 10 or less. Okay. But this is far more complicated than the one we looked at originally, which didn't have this methyl group there, and that only had the 4 sets, okay, due to the symmetry. Anyway, okay, enough on topicity. Let's move back to shift now. And shift values, we'll do a little bit on the board and then we'll get right to some examples. I've already been talking about shift. And there's a nice big table in your book. We'll have a table of some kind on test 4. So you don't need to memorize this, but you need to keep track of these. So we talk about shift. And let's look at proton NMR. If we have fluoromethane versus dimethyl ether versus trimethyl amine versus what? Ethane. So these are CH3 groups with what? Different heteroatoms on them. Heteroatom meaning non-carbon. So here we have fluoride, here I have oxygen, here I have a nitrogen. Okay, all 3 of the methyls are the same, but the shift now is going to be important. And then we'll reference it to ethane. And what we're going to look at here for the delta values is, if you do the NMR of that, it's a 4.3 ppm. This one here is a 3.2 ppm. This one's 2.2, and this one's 0.9. Okay? So what's the difference here? Notice we're going what? Well, we got to have the periodic table flipped around. This is all the way on the right side, right? The most electronegative. Then we have what? Oxygen, then we have nitrogen, and then we're to carbon, okay? What can we correlate this with? How about electronegativity? And let's see, how does this delta value change depending on the electronegativity of the atom that these hydrogens are nearby? What's the electronegativity of fluoride? 4.0 O on the Pauling scale. It's the most electronegative atom. Oxygen is also very electronegative, 0.5. This is not the shift value now. This is the electronegativity off the periodic table. Nitrogen, 3.0, and carbon, 2.5. So you see it directly parallels what? The presence of an electronegative group makes these shifted further what? Downfield, we say, to a higher value. How does that work? Well, we've got the fluoride and the 3 hydrogens there. Okay, draw the dipole moment here for that bond. Very polar covalent bond, polarized that way, which makes what? The carbon more partially positive. That's not the delta value. That's the partial charge there, partial negative, partial positive. And what this does here, these 3 hydrogens in the NMR, then we say are exposed to more of the external magnetic field. And what? They're shifted further downfield to a higher delta value. Because of this inductive electronic withdrawal, okay, the electron density or the cloud of electrons there is polarized toward the more electronegative atom. That leaves these little nuclei, as they spin, okay, more exposed to the external magnetic field, and you need a higher frequency in order to flip them out of resonance, okay? So we say that this is de-shielding. And that means it shifts to a higher frequency, a higher ppm. Notice here compared to ethane, that's up here close to TMS. TMS is what? It's 0, okay? That has a silicon on it. But now we have a carbon here, 0.9, very what? Not electronegative. So it's shifted up to a higher, or sorry, a lower frequency, being more shielded, closer to 0, closer to TMS. And that's due to what? The low electronegativity of carbon here. Okay, so these 6 hydrogens show up at 0.9. And we say that they're shielded. Okay? Because of the higher electron density, there's not an electronegative atom around. So these hydrogens, these alkyl hydrogens, will tend to be up here around 1 ppm. All right, let's look at another effect here. If we have multiple electronegative groups. So let's look at another series of compounds. Point out this effect. So proximity to electronegativity and the number of electronegative groups. So there's chloroform again. Okay, let's look at the shift value here. And how about methylene chloride? Dichloromethane, and we've already seen chloromethane, and let's compare this to methane. Now methane and ethane are hard to do because they're gases, okay, but you can condense them, pressurize them in the tube, do the NMR. Chloroform's fine, it's a liquid, 7.3 ppm. 5.3 for methylene chloride. So what do we notice here? Well, we got 3 electronegative halogens now. Very electronegative, making this very partially positive and making what this hydrogen extremely exposed to the external magnetic field, so it's a higher frequency to tip that out of resonance. Methylene chloride, there's 2, so 5.3. This one we've already got, what is it again, 3.1. And then methane, about the same as ethane there. So the number of electronegative groups being in proximity is another very important effect. That what leads to more de-shielding, higher frequency. Let's see another thing. How about hybridization? And this is another important factor here. We've got aromatic, benzene, those hydrogens. We have ethylene on an alkene, and we have alkane. Let's look at those 3 first of all. Aromatic, directly on a benzene, 7.3 ppm. Okay. On an alkene, 5.3. Let's see, directly parallel here. Don't get confused about it. These are different molecules now. And this one we've already got, 0.9. What about this one? So what we're looking at is hybridization, right? The aromatic ones here, and on the alkenes, what are those? sp2 hybridization. You're already thinking, what? That's 33% S character. So this is held a little closer to the carbon, which makes, again, this more exposed to the external magnetic field, a little more partially positive here. Same thing here, sp2 hybridized. Then I have sp, or alkyl hybridization, is up around 1. What about this one? Let's have a prediction on that. What's the hybridization on a terminal acetylene? Well, it's sp, right? So where should it be? Should it be up here higher at 7.3? Maybe in the middle here? Or further down here? What are you going to say? Let's see. Based on hybridization, you might be thinking, well, that's 50% S character. This should be what? Around 10 or maybe 12, right? Well, here's the shock for you. It's at 2.5 ppm. It's right in here. And so I have a big question mark for you. How does that work? Well, there's another effect we need to look at. It's obviously not just hybridization. It's another effect called diamagnetic anisotropy. Oh, there's a mouthful for you. And it's a technical term, a physics term. We'll just look at it from a practical point of view, looking at what this means for these pi electrons and how that affects the shift of the attached hydrogens. So we need to look in a little more depth there at this effect. So what do we have here? Diamagnetic anisotropy. What does that mean? Diamagnetic means pairs of electrons that are spin coupled, that's the diamagnetism. And anisotropy means in an external field they're arrayed in space with different regions that can affect the strength of that field. So it's kind of a technical term, but let's see what it means when we talk about benzene. Because the benzene one is really the one that really stands out, being at 7 to 8 ppm. So these hydrogens here, and there's of course 6 of them on benzene. And you remember the structure of benzene, you have these pi electrons, right? These are p atomic orbitals around here. And they're all fully delocalized both above and below the plane there. Well, what this does here in the large external magnetic field, okay, which has a directionality to it, a moment to that magnetic field, what establishes here is an electron ring current. And this current is going around the ring in this direction, okay? So picture those 6 pi electrons going around the ring. And why does it go around the ring in that direction? Because it creates field lines here. It's kind of a toroidal, 3-dimensional shape there. So you can imagine these field lines going all the way around. These one on the side is a magnetic field, okay? Magnetic fields are always perpendicular to the electrical fields. And the directionality of this magnetic field is such that these field lines are going in this direction. Okay, I think I got this correct. So this creates another little magnet, you could say. That's this arrow here, which is the sum of this toroidal magnetic field. I have a better graphic. We'll switch on the graphics in a second. But I think me drawing it kind of shows you the origin of what we're talking about. We have one electrical field. And remember, they always come in pairs. Electrical fields, magnetic fields, they're always perpendicular to each other. This is in a ring, so it's kind of a different shape. We've got a donut shape this way in the plane of the benzene. Then we have these toroidal field lines all the way around, pushing out to try to oppose the large external magnetic field. Well, the consequence is anisotropic. Depending on where you are in space, you have different effective fields that you feel. Okay. Let's put ourselves in the place of this hydrogen right here, or any of them on the side here. What do they feel? Well, they feel the extramagnetic field from the induced ring current. Okay. So this one here, you see the field lines are coming up like that. So these hydrogens on the external sides of a benzene will feel what? The magnetic field plus the extra field from the induced ring current and the toroidal, like I said, because it's in a ring that way. Okay, let's look at the overhead. What this means is what? This is shifted downfield. Okay, it's more de-shielded. Let's look at the graphics here up there. And here's your overall depiction of shift values, alkyl, around 1 or so. It can vary depending on whether it's a methyl, a methylene, or a methine, a little bit, kind of changes that way. If it's alpha to a carbonyl, it's still on a carbon here, and there's a carbon next door to the carbonyl. They're around 2.5, 2 or so. Here's our strange one, like I said, sp hybridized terminal acetylene, about 2.5. If it's alpha to an oxygen or a fluoride or a halide, what do we say? It's around 3 or so. Okay, so those are general things. Alkene, sp2, so the hybridization and this anisotropy effect come into play here. So we have the alkenyl and the aryl. They're around 5 for an alkene. We have the ring current, a bigger ring here, around 7 for aromatic. On the side of an aldehyde, now it's directly on the carbon that's part of the carbonyl. It's an aldehyde. So that's a very electropositive carbon, which makes that highly deshielded, and yeah, that's shifted way down to 9 to 10. On an alcohol, or carboxylic acid and amine, remember these we say are hydrogen exchangeable, so they'll always be singlets in a practical sense there, and they're directly on the heteroatom. So it kind of depends on the concentration there. They can be way down, 10 to 12. Usually an alcohol will be 3 to 4 range, but they can be variable depending on the concentration. They can vary. The more concentrated it is, they tend to be shifted a little bit further upfield. If they're more dilute, they tend to be a little bit further downfield. But it can be variable. You always see it as a singlet. And these can be exchanged easily with deuterium if you just wash it with D2O, for example. These will exchange out, and then the deuterium is silent in the NMR. Okay, that's not an NMR active nuclei. Only the protons, the H1. Anyway, that's the range there. Here's the diamagnetic anisotropy. If you can pronounce that, you get an A on the next test. No, I wish that was the case, but don't worry about that name. It just has to do with, pi electrons can create these ring currents, and that has an electrical field. That's the light blue here. And then the toroidal thing, and this is all the way around, a complete 3D donut structure, or the dashed orange lines there. And notice they set up to oppose, here's the field line for that induced mini-magnet from the current, which would be opposing the external magnetic field. So that's why I drew this out on the board that way. And what the hydrogen on the side feel is this extra little magnetic field from the ring current, and it could be substantial for benzene, all the way down to 7. This still doesn't answer the idea of the acetylene though, right? The acetylene's an anomaly, it's way upfield, 2.5. It goes against what we think about just hybridization. But you can see the pi electrons here in an alkene are similar. That's a much smaller little ring current there between the two. It does have these external little extra field lines which add to the external magnetic field. That's the orientation that way. But now, an acetylene has a different orientation because of the 2 pi bonds. It has barrel-shaped topology, and to oppose that external magnetic field, it flips up on end here, a different orientation. The electric current is around this direction here, the purple thing. That makes the magnetic field lines in this direction here, which you see what? It's actually subtracting from the magnetic field there, what it feels here. Those direction lines change their orientation. So it's an anisotropic effect, which actually is what? Subtracting to the magnetic field, which shifts it further upfield against the property of it just being based on the hybridization. This is sp hybridized, so it's 50% S character, which would make that more deshielded just based on that effect. But because of this change in the ring currents, it actually subtracts more from the magnetic field. You see these field lines here, and that will, instead of adding to the magnetic field, make high frequency, this lowers the frequency for a acetylene. Anyway, don't worry about the physics, you don't need to worry about that, but just recognize there are different concepts here that can affect the shift value. All right, let's get into, well, there it is there for the pi electrons effect there. And there are different ways to depict these charts. We've got a couple ways of putting it right on the ppm chart, so you can keep track of it that way. Okay, let's go back to this example, which is what? Tert-butyl methyl ether. Okay, so the two sets, there they are, resonating at 3 and 1.1 or so. And the height of these lines can be deceptive sometimes because the line thickness can kind of change. So the integration, here's the second characteristic of NMR. We need to integrate here, which is actually the integral. It takes another experiment to do this. And it measures the area under this peak here. And it applies an arbitrary unit number here. And you have to know something about the formula and figure things out here. So let's look at the formula of what we might expect for this molecule and see if we can make sense of the data here for integration. So we've got what? C, how many carbons do we have? 5, H, 12, O. Okay. You see that? Both the boards there?
I can't really see both,
Okay.
but
We'll kind of come down here first, maybe.
okay.
And what we see here, where would we get this data from? We get this from the mass spec. And I think it's 88 for the molecular weight there. And, you know, that just tells us we have 12 hydrogens maybe for this suspected formula here. But if we've got a structure like this that we propose, then when we go to the NMR, we expect to see what? The two sets. Okay? Now the integration is going to be different here. CH3, and how many here? 9, right? These 3 methyls here are the 2 tert-butyl all the same. So the integration here is 3 to 9. But it may not show up like that. It could be 6 to 18, okay? Or it could be what? 1 to 3. For the data here that came out of this experiment, it was what? 20 to 60. So what you can do experimentally, if you think that this one signal is just for one hydrogen, it might come out to 1, and then you divide this number, whatever it is arbitrarily, by 3, and you see you get down there to 1 to 3, or if you divide by another number, you get to 3 to 9, whatever. You have to play around with this. What we get from the integration then is just the ratio. We have to have some idea of what the structure might be to apply the absolute number which are in those sets. Okay? You see that? That can be kind of tricky. It's kind of an arbitrary thing. We have to measure that carefully and experiment with that to see how we might arrive at that. But if we had 60-20 here, but if we only had 12 hydrogens, you see the only thing that makes sense is 9 to 3, which is still 3 to 1, okay? It's still the same ratio. But it wouldn't make sense if we divided both of these by 20. We divide 20 by 20, we get 1. 20 into 60, we get 3. But that's not what the formula is. So we're always thinking about what the formula might be before we apply that. A lot of times we can identify a set in an NMR spectrum where we predict there's 1 hydrogen there. Then we can divide all the other numbers by whatever that value is for that 1 hydrogen, and then we get an indication of what it might be, but we'll double check that by looking at the formula. Does that make sense? And the more you work some problems, you'll see how that could be. Now let's do another problem here, and I'll start on the board here, and we'll start with the molecular formula and get an idea of what we're talking about. So here's one, C9H10O2. And we can see we've got aromatic. If we look in the NMR, and we'll go to that in a second here. And we can also see the mass spec gives us this molecular weight. Oh, I didn't write it down. But we also see in the NMR here, not only aromatic, we see some other shifts here, and the ratio is 5 to 2 to 3. And they're all singlets. So we kind of have to figure out what a structure might be there for that, depending on the shifts. Well, I'll show you the structure right now, and then we'll go to the spectra and see what it looks like. It's actually this acetate ester right here, okay? In the 3 sets, like I said, a lot of times these 5 aromatic ones on a monosubstituted benzene will all show up the same. And then this is also a singlet. It's different than the methyl here. And that's the 5 to 2 to 3 that you can figure out there. So let's go back up here. Isaac, sorry.
No worries.
I'm going to move you around quite a bit today, I'm sorry. And what do we see? Well, we see the ones down here at 7, and here's the arbitrary integral, 54. And then we see this one here, 23. Notice that's not exact. If it was exact, it would be 50, 20, and then 30. But yeah, it turned out the numerical values here, 33, 23, 54. And you kind of have to play around with it. Sometimes it's plus or minus a few units there, but they're all singlets. And also 5 ppm. This methylene right here is in between a benzene and it's alpha to that oxygen. And that's kind of an additive effect. It's next door to the benzene and it's right next door to the oxygen. So those two things together shift it even further downfield. If it was just alpha to the oxygen, it'd only be around 3.5. But because it's also next door to the benzene here, it's around 5. And then this one is the methyl group just next door to the carbonyl of your ester. Go back to the structure and you can see that again. Let's do splitting now. And yeah, we'll stay back on the board here, Isaac. So we want to look at J values. So far we've done what? We've done the delta value. Okay, we've done integration. So now what? The J value, or the splitting, to get the multiplicity of what the signals will actually look like. So these are the 3 things, okay? The 3 pieces of data we always put together to figure out, make sense of what the NMR structure is. So we already looked at this molecule. Remember last time? The actual sample with hydrogens in it that the physicists went over to the chemistry department supply shop and they gave them a sample of ethanol. And when they tuned up their spectrometer, they were amazed to see these splitting patterns. So splitting came along quite early. This methyl group here has what? 2 neighbors, so it shows up as a triplet. These are little multiplicities. This methylene has 3 neighbors, so it shows up as what? A quartet. Okay. This one stays as a singlet because it's hydrogen bonded. So there's your multiplicities here. What about the integration? 3 to 2 to 1. Okay. Let's see how we get these triplet, quartet, and we didn't have doublet, but we're going to get to that here in a second. Let's look at this molecule. So we have dibromo and a bromo there. So we have what? Tribromoethane. So we have how many sets of hydrogens here? We have methylene, 2 hydrogens here, and 1 hydrogen there. Okay. These 2 are the same. Okay. This one is different. These are actually, an antiotopic. You look at the topicity, that's not a stereocenter. If that were a stereocenter, these would be diastereotopic. Okay. So we only have 2 sets here. Let's first look at these 2 hydrogens right here. That's what we're going to observe. Okay. And when we observe those hydrogens, it'll have a characteristic frequency, which will give us our shift value. And their alpha just is 1 bromide, the 2 bromides are over here, so that shift I think is going to be at 4 ppm. Okay. This one here is next door to 2 hydrogens, so that shift's going to be 5.7. So these are different shifts, okay, 5.7 and 4 ppm. But what's the multiplicity pattern? How many neighbors do they have? Let's see. This one here has what? 1 neighbor. So the shift, if we didn't expect any splitting, would just look like that. And its position, delta value, would correspond to that frequency, you know. And it's characteristic of being alpha to 1 bromide. So yeah, it's around 4 ppm. However, what do you see here next door? Okay, this guy here can be, well, let's have it as a triangle here. That hydrogen's different. When we're irradiating here at 4 ppm, it's also seeing this proton, right, which has its little mini magnet, its nuclei is spinning, and that spin can either be spin up or spin down. There's 2 different states for that 1 hydrogen in the triangle right here. So we say it's plus 1/2 or minus 1/2. If it's in the spin up position, it's in the same orientation as the magnetic field. That's adding a little bit to the magnetic field that these two actually feel or see. So there's one position, once we have the J splitting here invoked, where it feels a little bit more and then a little bit less. Okay? So here's the original shift position, right at 4 ppm. And what you see is we have a little bit, what? Added to it. That's the spin 1/2 that it feels from its neighbor. Or that spin state can be down, which subtracts from the magnetic field. So with one neighbor, the n+1 rule, n equals 1, right? So what do we see for these two hydrogens right here? That's right, it's a doublet, okay? That's the key thing to keep in mind, okay? The splitting pattern is due to the extra little magnets that they feel next door, okay? Either adding or subtracting. And if you only have one neighbor, it has two spin states, up and down, okay? So it's a little doublet. And we'll see, we'll verify it in a second. But we're not done, right? We need to look at what? We need to look at the other guy here. Let's look at the methine hydrogen now, okay? So let's redraw the molecule. We'll treat these things separately now, go through it carefully. So we're going to observe right here, okay? In this one, we're going to observe what? It's 5.7 ppm. And what? It's next door to two hydrogens now, okay? And now they're in triangles, okay? So it's 5.7. What's going to happen there? Well, instead of being a singlet, it's going to see two different spin states. Now, how can we arrange those two spin states? Well, we can have two of them be +1/2, both lined up, or two of them both down, or one up, one down, or the other one up and the other one down. There's two different ways to have one up, one down. These spin states are kind of fun to keep track of. Let's see, if we have spin up, that's one way to do it. But we can also have spin up, spin down, or spin down, spin up, okay? Okay, those are two different states that could have adding to the magnetic field, or this one up, this one down, but there's another way to get this one. The probability is doubled here, spin down, spin up, okay? It's twice as likely to be this way as it is this way. And what's the other one? That's right, spin down, spin down. We have three different states. So what it actually looks like is what? A triplet, okay? Because it has two neighbors here. We're observing this guy, and what we see are this spin array here. Spin up, up. You see that's adding to the magnetic field. Right here, we're canceling it out, right? But this inner peak is large, and that's centered right on where we expect the shift to be, 5.7. And then this one, what, they're both subtracting from it, okay? What do we call this distance right here? This little difference in the frequency. We had it over here in the doublet too, right? This little difference in frequency, we call that the J value for the splitting. And it's usually a J3 value for most molecules where we're looking at this vicinal relationship. Notice there's 1, 2, 3 bonds intervening there. That's why it's J3 type coupling. And that's very typical for vicinal neighbors. And it's typically about 7 hertz, okay? That's kind of the average. It's not very much, it's a tiny amount. Remember, these are the extra little magnets. So this difference here would be this J value of about 7 hertz. Okay, but we can see it. So let's see. Let's look up here and see what we got. For tribromo ethane, I think you can see that there. There's our molecule we've been talking about. Look back at your notes. Look back at the board we just drew on there. Which one did we look at first? Oh, we looked at the doublet here. Remember? We said it was about 4 ppm. There it is. And sometimes you kind of blow these things up. So this is an inset thing of what that looks like. Sometimes you can't see them. The J value is very small. And there it is, this nice doublet, both adding and subtracting from the magnetic field due to the one neighbor there on that methine hydrogen. Now the triplets down here, why is it further downfield? Well, this methine hydrogen has what? 2 bromides, 2 electronegative groups, so it's further downfield, 5.5. And here's the triplet, because we have the 2 neighbors. And those spin states can be treated quantum mechanically The equations for it mathematically are very complicated. What I just showed you here with the spin up, spin down, and probabilities holds there. And you see a nice triplet, where the peak in the middle is what? 2 probability states. 2 down or 2 up, or just 1 probability, and then the middle one there. Sometimes the heights are a little bit different. You see this height, its inner height's a little bit higher, and notice it's leaning towards, coupled to something to the right, and you see this double, it's coupled to that inner peak here, leaning toward its coupling partner was a little bit higher there. Sometimes you can use that effect to tell whether it is. So the probabilities of spin states are not equally populated, and that has to do with the orientation of the magnetic field and what they're coupled to, which is kind of cool there. But triplet, doublet there. Let's go back to ethane. No, let's look at the spin states here in general here. So yeah, no neighbors, singlet, okay. 1 neighbor, doublet. So this is the n+1 rule. Triplet, we've talked about that. Quartet, we could draw that one out for you too. We saw that in ethanol. If there's 4 neighbors, this kind of goes beyond the structure though, because what, a methyl group has 3 neighbors, so we have to go beyond a typical structure. If we have 5, 6, or 7, we have higher order multiplets. Sometimes these are hard to tell or hard to see. If it's beyond 7, we just call it M for multiplet, and that's okay. But we'll get into this multiple coupling pattern. What I'd like to do now is come back down to the board and practice what we think some of these structures might look like. So I'm going to draw some structures, and we need to figure out how many signals are we going to see in the NMR. What's the delta value going to be? What's the integration going to be? And what's the J coupling, or the multiplicity, going to be? So for this one, we've got what? Just 1, 2 dibromoethane. How about this one? Bromo ethanol. And how about this one? A ketone. How about this ester? How about this? Propene. How about isopropyl bromide? Yeah, we got a few here, don't we? Propyl bromide, been showing that molecule. I think that's enough. Yeah. So pause the video here, see if you can figure out the expected number of sets, what is going to be the delta value for each set, how will they integrate, and what will be the multiplicity pattern. With these simpler, typical type of problems here, you should be able to handle this, or at least get in the ballpark. Sometimes the delta value is a little bit hard to say, but let's see how well you do. Okay, pause it and work on that. Okay, we are back, and so what do we expect here? How many sets do we have for this one? Right, just 1, because of the symmetry there. All 4 of those hydrogens are the same. You don't get splitting unless they're different sets. When the spectrometer irradiates this, these will all resonate at exactly the same frequency. You don't get any splitting. They'll all be excited and then decay back down to equilibrium at the same time. So no splitting, just a singlet. What will the delta value be? Well, it's about 3.0 ppm. Okay, that's singlet. Okay. How about this one? How many sets here? Yeah, 1, 2. Those are different now. Alpha to oxygen, alpha to bromide. And then that one is also different. Those 3 sets. Okay. They're all about, this one's about 3.0. This one's 3.5, and what will be the integration? 2 to 2 to 1, okay? What about the multiplicity pattern? These 2 have 2 neighbors, so what? Triplet for those 2, and what about those 2? 2 neighbors, triplet also. No splitting to that one, why? Because it's on a hydrogen bonding exchangeable hydrogen, and so they generally don't show up. It'll be a broad singlet, okay? What about the ketone here? We've got a methyl, a methylene, and a methyl. How many sets? Are the methyls the same? No. So we've got 3 sets, about 2.4, about 2.6 or so for that one, and about 1 ppm for that one. Those are all the ppm values. Integration would be what? 2 to 2 to 3. What about multiplicity here? Methyl group, how many neighbors? 0. So singlet for this guy. How about this one? How many neighbors? 3. So it'll show up as a quartet. Very good. And what about that one? 2 neighbors, triplet. Okay. So it tells you a lot about the molecule. Okay, there aren't many other molecules that fit that bill. And especially if you add in the mass spec and IR data, you can tell that that is 2-butanone. Okay, different than the aldehyde, different than an ester or ether or anything there. This set of data really delineates what that structure needs to be. All right, let's go on to this ester here. How many sets? 1, 2, 3, 4 sets. Yep. This one will be about 1 ppm. This one about 2.4. This one alpha to this oxygen, and it's alpha to an ester oxygen. This is electron withdrawn due to the resonance effect here. This will tend to be about 4.5, a little bit higher than normal. This one here probably around 1.5 or so. Again, it's kind of close. And this proximity effect to a heteroatom kind of tails off quickly, so this would be much more shielded than this one. Highly de-shielded those. And what do you get? 3 to 2 to 2 to 3 for the integration. And what about the multiplicity? How many neighbors here? 2. Yep, you get this triplet. How many there? 3, so quartet. Yep, and then here again, what do we have? Quartet. Another quartet. Notice this quartet's down at 2.4. This quartet's up at 4.5. Okay, so you see those multiplicities propagating, but the shift is also superimposed on there, right? It's a different set. And this one here, also what, a triplet? But that triplet here is 1.5. This one's at 1, so those might be close to each other, but again, different ones. Okay. What about propene? Yeah, the methyl group here. It's next door to an alkene. It's not right on the alkene, so this will be about 2.5. What about this hydrogen, and this hydrogen? How many total do we have in these sets? 1, 2, 3, 4. Notice this hydrogen is what? Fixed being cis to the methyl. This hydrogen is fixed being trans. We're not rotating around this bond to exchange those. So how many sets do we have? 4. This one's about 5.5 ppm. Okay, it's a methine, a vinyl, or alkenyl hydrogen. These are also vinyl hydrogens here, but they've got hydrogen mixers on the terminal end of it. The cis one, it's very similar. They're both around 5, and sometimes these can be right on top of each other, but they'll have different splitting patterns. Let's see, this one has how many neighbors? 1, so right, it's a doublet. Okay. This one here, how many neighbors? Well, it has 3 here, it'll be a quartet. But notice it's also split by this one and that one, vicinally. So it'll be a quartet of doublets of doublets. Now this is a multiple spin system. This gets more complicated. This is the so-called n+1 times m+1 rule. And it's not only split to another set here, it's also split to another set, so you get a 3 pattern there. So in theory, it might show up. We'll have to analyze a specific example to see that with an alkene. But yeah, 4 patterns and complex coupling here. Now what about this one here? Well, it's got this one next door. That's a J2 coupling through 2 bonds. And because they're different, you see J2 coupling. It'll be a doublet. And it's also coupled here vicinally, J3, a doublet of doublets for that guy. It's not triplets, not coupled to that guy. Same thing for this one, doublet of doublets. Sometimes they're right on top of each other, and you'll just see a bigger signal there. We'll look at some examples that'll help you out there. This one's a little more straightforward, you could say, but watch out. The coupling here is a little complex. Let's see, this one here is going to be about 1 ppm. This is about 2, and what? This is about 3 there. And what's the integration? 3 to 2 to 2. That's easy to see. What's your multiplicity here? Triplet? Let's do this one first over there. 2 neighbors, also a triplet. Okay. And what about this guy here? This methylene at 2. Well, it's a quartet that way and a triplet that way. We've got a complex pattern there that makes that a little tricky. The isopropyl bromide, though, if we just move the bromide over, how many sets do we have? 1 for the methine, and these 2 methyls are the same. So we have 2, right? This one here is going to be about 3.5. move it a little bit downfield because it's methine, okay? And these here are going to be around 2 or 1.6 or so. And then what about the multiplicity? Let's see, this one hydrogen has how many neighbors? Count them all up. 1, 2, 3, 4, 5, 6. Okay, you count up all of them. And so it's going to show up as a heptet, okay? A 7-line pattern. Okay, the spin states all add up quantum mechanically, and you can derive what that might look like. What about the methyls here? How many non-equivalent neighbors does it have? Just the one. So these will show up at the same spot, but it'll be what? A big doublet, okay? And the integration will be what? 1 to, what, for the 2 there, to 6, okay? So you can see that molecule is easy to tell apart from that molecule based on the number of sets, the shift in the multiplicity. All right, let's look at maybe one idea here on the board. Let's do this guy right here, is a quartet triplets. In fact, let's make some more room over here. Now we'll go back up to the board there. I want to look at that pattern there and see this n plus 1 times n plus 1 if we have a complex splitting pattern. So these two right here are split as a quartet this way, and what this way over here is a triplet. Now, you can do this different ways to analyze this, okay? The book says this is n plus 1 times m plus 1 rule. So with 3 neighbors over here, what, this has a 4-line pattern, the quartet. And this one over here has 2 neighbors, so it's a 3-line pattern, or a triplet. How do you get at this, and how do you think about this theoretically? Well, you can do the large J value first, okay? And the J value is the coupling constant, or the space between the lines. And let's say this one was really large at first. Let's do the triplet first, okay? So if it was coupled over here, say like 20 hertz, okay? This 20 hertz would be this distance right here. And then let's say the quartet value is really small. Let's say it's like 3 hertz, okay, for the quartet. So 20 hertz there, and then 3 here. Then we get this, okay? Each one of these 3 lines out of the triplet would be split into quartets. Yeah, I need 4. Okay, yeah, Isaac caught me on that one. That's good. And they'd have the same distance in the lines. The distance would all be 3 there. And let's see what we get to. Well, we get 3 here. Yeah, how many lines total is that? Add them all up. 3 times 4 is 12, right? Is that what we get? 3 times 4, yeah, 12. Ouch, okay. If the couplings are different, if one is large and the other is small, sometimes you can see all the lines distinct. But let's say both of them, the quartet and the triplet, the J value is around 7 hertz. Okay, hopefully I can do this. This might get a little messy. Isaac might have to help me out here. So the first one we're going to do is the quartet. And it's going to look like this. Okay, and that's all around 7. Okay. Now each one of these has to be split into 3. So that's the quartet. We're doing the quartet first. It's just easier to do the larger multiplicity first. Now we need to split each one of these into what? A triplet. That would look like that. For that one. This one would also be a triplet. 3-line pattern. But notice what? We're congruent here. Because the 2 J values are both around 7. So this one's also split 3. I'm doing that right. Isaac's nodding his head. I think I'm on the right track. Yeah, it helps to be an artist here. Or you can do the quantum mechanics, do the full-blown equation and figure this out. How many lines do we have now? Not 12, where they're different splitting values. Here, they're both 7. So this distance here is 7, and we have 1, 2, 3, 4, 5, 6. It's an apparent 6-line pattern. Yay, that's a lot easier to keep track of because what? These two hydrogens have how many neighbors? 1, 2, 3, 4, 5. So what? The N plus rule holds here. If you have multiple splitting partners, it's okay. Just if they're equivalently split, if they're all about 7 hertz, which is true for most ring open compounds like this, because you can rotate around all those bonds and the couplings average out. So if they're all around 7 here, it just comes out to 5 neighbors plus 1, comes out to a hextet or a sextet, okay, 6-line pattern. And here you see it. It's an apparent hextet because actually the couplings are happening at the quartet and triplet level, but because of the distance here, the splitting patterns, the J values are all about the same. 6 is a lot easier to keep track of than 12. Let's look at the actual spectra for this molecule, and hopefully it'll become a little more clear. So going up there again, Isaac, so we've got some typical splitting patterns here for 2 methynes together, 2 doublets. And then we have a methylene and a methine, that will be a triplet doublet. And we have 2 methylenes, 2 triplets. So these patterns start to be repetitive. So you see different patterns, you can tell what type of substructure might be in your molecule. And ethyl here, we've seen this in ethanol, right? Methylene and methyl, that's a quartet triplet. And then a methine methyl, yeah, quartet doublet. So this tells you the peaks and the splittings and then the patterns there. I think you can look through that table and see from your book. So here's the molecules we just looked at, these propyl bromides. Here's isopropyl bromide with what? That methine here, alpha to the bromide, so it shifted down to 4 ppm. Maybe I had that wrong. What did I say before? I said 3.5. That was just a guess. The actual molecule is 4.2. Okay. And how many lines in the pattern? Well, it has what? 6 neighbors. So it is a 1, 2, 3, 4, 5, 6, 7 line pattern. The ones on the outside are really tiny. That's because the probability of the spin states being subtracting here or neutral, if you have an equal number of spins up and down, that's more highly probable. And there's different ways to array that spin state. You see it right on the frequency there. So you have to kind of analyze that sometime. We might just bail out and call that a multiplet. So we may not be able to see the full multiplicity as a heptet. And that's okay. Multiplet's okay, unless you can distinctly see all the patterns. This one you can clearly see as a doublet, right? Because these 2 methyls are just with 1 neighbor here. It integrates, 6 to 1, so the integration helps us out. But if you have an isopropyl group, you're probably going to see a big doublet down here around 1 and a little multiplet further downfield, okay? So doublet and then heptet, that's probably an isopropyl functionality in your molecule. And here's the other one we've been analyzing, a little bit more complexity there. We've got the triplet here for being alpha to the bromide, shifted 3.3. And then we have, let's look at this one first, the triplet over here, which is the methyl on the end, that integrates 3 to 2. And then the methylene in the middle here is this, 6-line pattern, because the couplings are the same. Actually, it is a quartet of triplets, but because the spin states line up equally there, the J values being approximately 7, it's this 6-line pattern that we analyzed on the board. Okay, let's see. Let's try to fit one more in. I know we might be going a little bit over, but let's go back to the board here, and we're going to see a couple other molecules real quick. I think we can do these pretty quick. We've got a feel for this now. We're putting the whole thing together, right? Shift, integration, and coupling. Next time we're going to keep working a lot of problems, so we'll look at NMR data and try to propose structures for it. But the first one I'd like to look at here is this molecule. So we have a vinyl acetate ester. How many non-equivalent sets do we have? Well, these are all different. We have 3 different ones on this alkene. Okay? These 2 are trans to each other. These 2 are cis. These 2 are geminal to each other. Okay? These are vicinal relationships. This is some trans. This is that geminal thing being a terminal alkene. And then, of course, this set over here is distinct. Okay? Let's look at the data and expect to see what we have here. If we look at this one here, how many neighbors does it have? 1, 2. So it's going to be a doublet of doublets. Okay. This one here, also a doublet of doublets. Okay. And this one here, doublet of doublets. Oh, we're going crazy here with the doublets. Okay. The J value here, if it's 3 in trans, is about 20 hertz. So we can tell this relationship here by the J value. And we'll see this larger coupling both in this signal here and that signal there. This one here is what? Cis to it. And then this one is vicinal to it. So we'll see that vicinal coupling here. But this one will have a J3 that's what? Cis to it. And that cis value is a lot smaller. It's only 6 hertz. Okay? This geminal coupling, though, can usually be considered to be quite small. Geminal coupling, and that's a J2 value between these two right here. It's usually quite small. Okay? We'll see what the actual data looks like, but let's first look at this one right here and see what we expect to see there. Well, that first splitting will be large. It'll be 20 hertz for the J value. And that's coupling to this neighbor here, right? Viscally, that's that J3 trans thing. And that's because electronically, this sigma bond is set up next door to the sigma star right here. And so these tend to be strongly coupled geometrically because they're fixed being trans. Don't worry about that effects. Just know that trans coupling J3 value is going to be large. So that's that doublet right there we see. And then this guy is also coupled to this one here, which is this cis coupling, which is 6 hertz. So that's what we expect for that one. Okay. 6 hertz. Okay, so also a doublet there. Plus, this guy is next door to the oxygen here, so we expect that to be shifted further downfield. It actually comes out to 7.2 ppm. Okay. Now let's do a couple of the others here, and then we'll show the actual spectra for it. Sorry, we gotta move over here. And then we'll be going up there, and we're almost done. Do this last one here. So let's see, how about this one right here? So I already did that one right there on the acetate. We won't worry about the acetate. We already did this one here. Let's look at this one right here. So it's also got this large doublet, 20 hertz, okay, for the J value. It's also got this geminal coupling here. And this geminal coupling here is only 3 hertz. And this is that J2 coupling, okay? 1, 2 bonds coupled to that one. They are different. A lot of times they're the same, depending on symmetry. You notice this hydrogen is cis to that acetate. This one's trans to that acetate. So these are different, and we have 20, and then we have 3. So 20, we'll see that same large 20 here. Then we only see this really tiny 3 in there. So again, it's a doublet of doublets, but it'll be a little bit different with a smaller space there. And also, this is out on the end, so that shifts there. The delta value is 4.9 ppm. All right, let's look at this one. We've done those two. Let's look at this one now. So what do we see? We see the cis coupling right here, and we said that's smaller. Okay, it's 6 hertz, and this one we just said is what, 3 hertz. Okay, so again, it's a double of doublets, but it's only 6, and then what, 3. Okay, and we can figure out the shift of this. We'll see it in a second. The shift here is 4.6 delta. All right, let's go up here and see if we got this right. Sorry, just one more. We're almost done. Sorry, it's a little longer, this video. So we got this one here, which is the vinyl hydrogen HD, as we're labeling it. Remember that one has the trans and the cis coupling here. And this is the 20, and then the 6, okay? So you can kind of see that large coupling. The large 20 is from that one, and then 2 lines over, that's 20. But you can, look at the patterns we drew on the board to see that. And that's the furthest one downfield, right? Because it's next door to the oxygen here. And it's also a methine hydrogen, right? It's more substituted. And then the terminal hydrogens here, C and D, are further what? Upfield. And here's our, again, you see the trans, the big 20 couplings right there. Okay, and that's right here, 20 there. And then the super small one, 3 Hertz right there to its geminal partner there, the C proton. And you can see that smaller pattern there. Still have the 20, but the very small second doublet. So it's a doublet of doublets. Okay. And then C here just has the trans, which is about 6 Hertz. And then the also very small vicinal one at 3. So it's much more compressed there. But you see those very distinct. 3 different signals on the vinyl proton, double of doubles. This one's further downfield because it's closer to the oxygen. Okay, additive effect there. And here's our acetate, our 3 equivalent hydrogens right there, HA, keeping track of. What's the integration? 3 to 1 to 1 to 1. The multiplicity pattern and the magnitude of those coupling constants. That's an advanced topic, okay? This is the trickier topic, keeping track of the magnitude of the coupling. But multiplicity tells us how many neighbors, combined, of course, with integration and what? The shift position. And we'll review that and work a bunch of problems next time. Very good. Thanks for hanging in there. Keep studying, and we'll see you next time. Very good.